In this fourth and final video, we reflect on what we've seen in the previous three, and then make some concluding remarks. The mathematical problems that we've seen concern prime numbers, and many mathematical problems concern prime numbers of that form which are easy to understand but remain unsolved. They remain as conjectures which are thought to be true but not yet proven. One either has to prove a statement for all cases or find a counterexample to disprove a statement. For example, we know there are infinitely many whole number solutions x, y, z to x squared plus y squared is z squared. These are called the Pythagorean triples, and there are three examples given there. You will probably be familiar with Pythagorean triples and the statement above from what is known as Fermat's last theorem. Fermat's last theorem says that for powers larger than 2, there are no whole number solutions to that equation. So there are no positive whole number solutions x, y, z to x to the n plus y to the n is z to the n for n being 3, 4, 5 and so on. So this is known as Fermat's last theorem, but actually it was not a theorem initially, although it was stated by Fermat as being true, but he did not prove it. So for a long time it was a conjecture, thought to be true but not proven. But more recently, using very high-powered mathematics, Andrew Wiles has proved Fermat's last theorem. So it's known that there are no positive whole number solutions x, y, z to x to the n plus y to the n is z to the n for n being 3, 4, 5 and so on. So for all positive integers from 3 onwards. But if n is 2, there are infinitely many whole number solutions. Often new mathematics is developed when tackling and solving problems which can then shine a light on other unsolved problems and other important applications. So just because the problem is straightforward to understand, the mathematics involved may be very complex to prove a result, and that mathematics may be useful in other applications. So we always strive for new knowledge in mathematics. Finding large prime numbers is actually very important to all of our daily lives. For example, if you use your favourite search engine and type in prime numbers and public key cryptography, you will see an explanation as to why large prime numbers are important. And indeed, the little padlock associated with most of the secure websites that you use relies on the existence of very large prime numbers. I'm going to conclude with an interesting problem concerning magic squares. Magic squares are squares in which the sum of the numbers in the row or the columns or the leading diagonals will be the same value. In some cases, if one considers 4 adjacent numbers in a block, they also sum to the same value. So in a 4 by 4 magic square, every line of 4 numbers, 4 rows, 4 columns and the 2 diagonals have the same constant total. The example above only contains prime numbers, so I'm going to call that a prime magic square. And it's the smallest possible total, 120, for a 4 by 4 magic square comprising only 4 primes. If one wishes to construct a 4x4 prime magic square where the 16 primes are consecutive in the list of prime numbers, one has to go a little bit further on and start with 31, but from 31 onwards, the 16 consecutive primes in the list of primes can be arranged in that square such that the sum of each row, column, and the two diagonals will be the same value. And that constant total is a little more than 120, it's 258. We can now ask the same question for a smaller square, a 3x3 magic square, where again the same property that the sum of all the numbers in a row or a column or the two diagonals is the same value. In this case, we want a prime magic square, so all the numbers in the square must be prime numbers. And you can see here the example with the smallest constant total happens to be 177. It starts at 5 and goes through to 113. But those numbers are not consecutive primes in the list of primes. So what is the smallest 3x3 prime magic square with the lowest total for row, column and diagonal sums, where the prime numbers are 9 consecutive primes in the list of primes? Well, you can pause the video and see if you can work it out. And once you've had a go and you've solved the problem, you will see the answer on the next page. Or if you struggle or you decide just to find out what the answer is, then don't pause and move on. And the answer is this. So if you try to find 9 consecutive prime numbers in the list of primes to arrange them in a magic square with the same row, column and diagonal sum, you have to go a long way through the list. And you will see an interesting pattern that they all begin with 1480028, and then they only differ by the last 3 digits. So never be surprised by the power of mathematics and what you will discover. Thank you for your attention.